How's it going, Accelerated Chemistry? This is Mr. Spurk, and this is your Chapter 18, Section 4 notes over solubility equilibrium. We know that there are some ionic compounds that dissolve in water and others that do not, and you should review your solubility rules for this reason. Most insoluble ionic compounds will actually dissolve to some extent in water. These compounds are said to be slightly soluble in water. An equilibrium is established between the solid and the dissolved ions in the saturated solution. To compare the solubility of salts, it is useful to have a constant that reflects only the concentrations of the dissolved ions. This constant is called the solubility product constant, or KSP. It is equal to the product of the concentrations of the ions each raised to a power equal to the coefficient of the ion in the dissociation equation. The smaller the numerical value of the solubility product constant, the lower the solubility of the compound. So what is the concentration of lead ions and chromate ions in a saturated solution of lead-2 chromate at 25 degrees Celsius? So let's first think about what our equation is. When we take lead chromate, which is PbCrO4, and dissolve it in water, it's going to break up into its two ions, Pb2+, and CrO4, 2-. KSP is equal to the concentration of ion A raised to the A power times the concentration of B to the B power. So what we have here, what we're going to set up is the KSP equals the concentration of Pb2+, and that's just raised to the first because we don't have any coefficient, times the concentration of CrO4, 2-. We know the KSP value is 1.8 times 10 to the negative 14. It's a really crappy looking 14. Let's go for round 2. Not much better, but we'll go with it. And remember that value means how soluble it is in water. This is a very small number, so this compound is not very soluble in water. So we set that equal again to Pb2+ times CrO4, 2-. Now when we look at our equation up here, we see that these are in a 1-to-1 mole ratio, so they're equivalent. Their concentrations, when dissolved, will be equal. But right now in our mathematical equation down below, we have two unknowns. But since they're equal, we can set them equal to one another. So we can say this is Pb2+ times the concentration of Pb2+. And like I said, that's because they're in a 1-to-1 mole ratio. We know that they are equivalent. So we can say that they're equal. So 1.8 times 10 to the negative 14th equals Pb2+ squared. And this is just so we can have one unknown. We're going to bring this up here. So now we have one. I'm just going to rewrite this. So that should just be squared. So when we need to solve for this mathematically, we can take the square root of both sides, because we know that what we do to one side, we have to do to the other. So we are left with 1.3 times 10 to the negative 7 molar, and that is the concentration of Pb2+. But we also know that that is also equal to the concentration of CrO4, 2-. So the next thing we want to talk about is the common ion effect. In a saturated solution of lead-2 chromate, an equilibrium is established between the solid lead-2 chromate and its ions in solution. So what would happen if you added some lead nitrate to this solution? So if we added lead nitrate, let's think about that. We know that nitrates are soluble. So when we put lead nitrate into solution, we're going to get more lead ions, more Pb2+. So if we are adding more Pb2+, we're going to shift the equilibrium to the left, and we're going to see more PbCrO4 solid formed. So what would happen is our reaction would look like this, and as we add lead to nitrate, it's actually going to shift back and form back into a solid down at the bottom of the flask. In this example, the lead is the common ion between the lead to nitrate and the lead to chromate. A common ion is an ion that is found in both ionic compounds in a solution. The lowering of the solubility of an ionic compound as a result of the addition of a common ion is called the common ion effect. So let's find the equilibrium concentrations in the presence of a common ion. So small amounts of silver bromide can be added to the lenses used for eyeglasses. The silver bromide causes the lenses to darken in the presence of large amounts of UV light. You may have seen somebody with glasses like this. When they walk outside, they get darker. The KSP of silver bromide is 5.0 times 10 to the negative 13. What is the concentration of the bromide ion in a 1 liter saturated solution of AgBr to which 0.02 moles of AgNO3 is added? So things that we know that the KSP for this AgBr solution is 5.0 times 10 to the negative 13. And we also know that we are adding 0.020 moles of AgNO3. So what we can do here is set up our KSP equation. So we know for this reaction that KSP is going to be equal to Ag2 plus or Ag plus times Br minus. And remember, we know the KSP, 5.0 times 10 to the negative 13. And we know that we're adding 0.02 moles. And we know that this is also a 1 liter solution. So we have 0.020 molar times the concentration of the bromide ion. And that's what we're looking for. So we can just divide both sides by 0.020 molar to get the bromide ion concentration on its own. And we get 2.5 times 10 to the negative 11 molar. So there's a lot more Ag plus ions in solution now. And that makes sense because we added 0.02 moles to a solution that already had some Ag plus ions. So this is the new concentration of the bromide ions. A precipitate will form if the product of the concentration of two ions in the mixture is greater than the KSP value for the compound formed from the ions. So if the concentrations multiplied together, the product, is greater than KSP, there will be a precipitate. So this question says, does a precipitate form when 1 liter of 0.0004 molar magnesium nitrate is mixed with 0.0002 molar NaOH? And we know that the KSP for magnesium hydroxide, which would be the solid formed here, is 8.9 times 10 to the negative 12. So what we're looking at is we're adding together MgNO3 2 plus NaOH. This reaction is going to look like MgOH2. And we know from our solubility rules that this should be a solid, plus NaNO3, which is going to be aqueous. And to balance our equation, we need a 2 here and a 2 there. So what we need to determine is, will this precipitate actually form? And to do that, we multiply we're going to find the product of the concentration of the two ions mixed together. So we're going to add together the concentrations of Mg and OH minus. Alright, so what we're going to do here is we're going to multiply together the concentration of Mg2 plus and OH minus. So Mg2 plus times OH minus, but in MgOH there are two of these, so we have to square that. So we take their concentrations, 0.0004 molar times 0.0002 molar, square that, and when we multiply these together, we get 1.6 times 10 to the negative 11. This value is greater than 1.6 times 10 to the negative 11 is greater than the KSP value given to us. So what that means is that a precipitate will form. Alright, so in review, the smaller the value of the solubility product constant, the lower the solubility of the compound. A precipitate will form if the product of the concentrations of two ions in the mixture is greater than the KSP value of the compound formed from the ions. And lastly, KSP is equal to the concentration of A times the coefficient of A times the concentration of B times the coefficient of B. Alright, as always, all the information on these slides has been acquired and adapted from Pearson Chemistry, 2012 edition of the textbook, the resources CD, and pearsonchem.com. Have a great rest of your day.